Okay, great. Yes. All right. So today we'll spend time talking about principal component analysis. In other words, it's our first of 2 weeks on unsupervised learning. So before this, well, the motivation of these two XKCD comics is on the left. I saw, well, how we choose our axes is an important modeling choice, right? So a few weeks ago, we had this fruit on 2D, and this is like things you can do in life on 2D. Informative choices of axes can reflect basically your value and the patterns in the data. On the right-hand side, I guess the takeaway for our class is that linear combinations of objects, mathematical objects or physical objects, they can be useful at times, and they can be like misinterpreted or dangerous at times. I've certainly personally used the spork to eat, and I find it useful, especially in fast food outlets. But yeah, look, what happens if you take it to the extreme, and we are going to do that in this in today's lecture. So okay, principal component analysis. We are going to start with a brief recap of eigenvalues and eigenvectors of symmetric matrices, which is foundation of PCA, and then we're going to look at two alternative formulations of PCA and how we apply it, and then extensions. We're going to basically look anything, right? Anyone asking a question? By the way, you're welcome to interrupt me and ask questions. So in terms of the extensions of PCA, we are going to basically look at PCA for high dimensional data n less than d in a little bit of detail. So there is a thing called kernel PCA. We're not going to be able to cover it because we haven't talked about kernels, but this is so this might be in assignment 2, probably, once we're finished writing assignment 2. And then probabilistic PCA, we will not look in detail, let me just say. We'll just briefly look at the definition of it. Actually, I'll just say brief. You won't be held responsible for like knowing all the material in your head. And needless to say, this week you are responsible for quiz. That's open basically today, 12 until Wednesday, like end of day anywhere on Earth. It should be easy. So don't be too nervous, and you have 2 hours from the beginning of your attempt. And it's only 2% of the grade for those of you who are not auditing. So don't worry if you sort of do one more or one less question than you expected. So the main purpose is to give somebody, like people, some exercise and early feedback. Right? So let's get started. So the eigenvectors and eigenvalues are useful concepts. And to be honest, I didn't know how useful they are until when I learned this chunk of content, until I learned PCA. Right. So this material is covered in a bit more detail in Appendix C. What's nice about Appendix C is that it also provides proofs of these basic facts, mathematical facts, within the limits of a few pages, which I think is a very good thing. We're not going to go through all of that, otherwise half of a lecture will be taken. So I'm just going to go through a few key facts and leave you to read it. So the definition of eigenvalues and eigenvectors are the following. It basically says if an eigenvector right multiplied by the matrix equal to a scalar multiplication of the matrix itself. Basically, the eigenvector is an invariant factor of the matrix. And then we can also write it in matrix form. If we basically put all the eigenvectors in a big matrix U, then the two matrix products A times U equals U times lambda, where lambda is this diagonal matrix of that consists of the eigenvalues on the diagonal and 0 as well, right? So for symmetric matrices, the eigenvectors can be chosen as orthogonal to each other. So if we, and what that means is, well, the eigenvectors are orthonormal, and U transpose is the identity matrix. What this means is that if we multiply C.38 on either side with U transpose or the inverse of U, we get the following expression, right? The big matrix A equals U lambda U transpose. And fairly interestingly, we can expand that in some summation form using the fact that the eigenvectors are also normal, and then the big lambda matrix is diagonal. We can write basically it's a weighted sum of the outer products of the eigenvectors, and the weights are the eigenvalues. So what this means is that the vectors are essentially the decompositions of A, right? What's also nice about this is that the inverse of A has exactly the same form, except the weights in the summation is 1 over lambda. In other words, the determinant of A is a product of its eigenvalues, and the determinant of inverse of A is the product of the inverse of the eigenvalues, right? So here we're using M as right. So for symmetric matrices of A, eigenvalues are real. In general, the eigenvalues of any square matrix are not necessarily real. There can be complex numbers. And A is positive semi-definite if all eigenvalues are greater or equal to 0. So for any real symmetric matrices, it's not guaranteed that the eigenvalues are greater or equal to 0, right? So there is a fact though. So for say data matrix X, right? For some X, for any X matrix, or actually let's write it in for a set of data vectors, the covariance matrix of X is positive semi-definite. I will show this. This is easily shown with the set of like matrix qualities here. And the reason we're talking about this is to lead into our discussion about continuous latent variables. So what does this mean? So to me, this way of structuring machine learning content is sort of interesting and unusual in a sense. So parallel to continuous latent variables, there is discrete latent variable models, which we will see next week. And very often in a typical machine learning class, the discrete version is introduced first, and it's also called clustering as an introduction to unsupervised machine learning. In the current setting, we're introducing continuous latent variables first because it connects well with the neural network content that we saw last week, as we will cover a version about nonlinear latent variable models and neural networks in the Friday session. So what continuous latent variable model does is it aims to discover the inherent structures of the data set. So the idea is that despite some of many observed data sets are high dimensional, they only have a small degree of freedom due to the underlying physical processes, such as in the book, the oil flow data set. It has 12 measurements, but the underlying physical process only have 2 dimensions of freedom. Right. And then some of the data sets, such as the written digits, have depending 256 pixel values, but there's only a few inherent transformations of digits that are sort of physically make sense, such as the size of the digit, the rotation, and the shifts of the digit. Right. So in these cases, the data can live in a low-dimensional subspace when they can be linear, like linear transforms of original data space, which is what PCA aim to model. They can also be nonlinear, where it's often called a manifold. So if you see the word manifold, it's a big word. Don't get scared. It's a notion of a subspace that's not linear. Think about a banded sheet of paper in 3D. Right. The other set of motivations is concerned with the dimensions of the data can be redundant with respect to each other. Meaning if we have a handwritten digit, let's say 2, then we know that, well, for images in general, neighboring pixels are generally tend to be more similar than non-neighboring pixels, right? So if there is a pixel that has a stroke that's written over, then at least one of the neighboring pixels will be written over, because these digits tend to be like form a continuous, tend to be done with a continuous stroke. So, and then if we know what these fewer dimensions are, they can make the data set easier to explain. And then if we can examine the transformations, then it will help us interpret what's happening with the data set. Moreover, reducing the number of dimensions would help downstream modeling and visualization tasks. I would say that in machine learning these days, it's not necessary that one want to reduce the number of redundant dimensions. For example, things like neural networks and logistic regression are quite resilient to larger input dimensions that are mutually redundant. Sometimes that's even preferred. But on the other hand, if you're visualizing your data set, despite there are much better visualization techniques available, a lot of the cases you're still using PCA first, something classic like PCA. For example, if you use what's called T-stochastic neighbor embedding, nicknamed TSNE, if you look at the neural network literature, you will encounter this for sure. It starts with PCA, running PCA on your high-dimensional data. Let's say if your data is, say, embedded of the 1048 dimensions, you do PCA down to about 50 dimensions, and then you run it through the TSNE. And in some cases, for example, in deep learning around 2010, people have found that unsupervised pre-training helps subsequent supervised training, meaning that like you don't supervise train end-to-end, but you run an unsupervised stage with PCA or the nonlinear version, and then do supervised training. That seems to work better. There is this note about one can visualize. Yeah, as humans, we can only visualize in 2 or 3 dimensions. So, for example, approaches like TSNE can help us pack high-dimensional data into 2D and still make sense. And there are, I would say, there are many good online visualizers nowadays. You can go have a play. So let's first try and define what principal analysis, component analysis is, or what the overall goals are, without going into the math. So principal component analysis is the simplest continuous latent variable model, right? It assumes that the data lives in a higher dimensional space, in this case 2D in the picture. Well, when we live in 2D, we want to reduce the dimensionality, we can only like find 1 dimension, right? So more importantly, both the observations and the latent variables are Gaussian. And we assume that we find this 1-dimensional subspace that are important or principal, right, by linear transformations. So in pictures, it looks like the following. So in 2D, we seek a space of low dimensionality known as the principal subspace, and denoted by this magenta line, such that if we orthogonally project the data points in red onto this principal dimension, now we need to state the objective, right? So for PCA, there are 2 different objectives possible. So it maximizes the variance of the projected points. Basically, the green points are maximally spread out with respect to each other. Turns out there is an alternative definition is to minimize the sum of squares of the projected errors, meaning the sum of the 2 norm or square norm of these blue lines are actually minimized. And turns out that these 2 formulations are equivalent. So that's quite nice. We've been looking at equivalent formulations in supervised learning for a few rounds now. And we encountered this at the very beginning of unsupervised learning. Before we dive into that, let's look at why this is important. Oh, first of all, let's make a note of the terminology, right? So principal component analysis it's written with the word principal, but not principal, like not this very, I misspelled it, sorry. Like not principal, because the word principal with P ending in AL refers to first of highest rank of importance, such as chief. But principal ending in LE is a basic truth, law, or assumption. If you're like me, sort of learn this area in American English, it might be more confusing than otherwise. So the other way to remember this is that the word principal is in principal component analysis, this it's an adjective, but the word principal that ends in LE, it's only a noun. All right. Turns out this is a very old approach. It's been independently discovered twice, at least twice, actually more than twice, as we see downstairs. The two well-known versions are from Hotelling in 1933. And it is the maximum variance projection formulation. So more than 30 years before that, it's also articulated by Pearson. So this is the statistician Pearson that we compute Pearson correlation with. So Pearson have stated the minimum error formulation, right, in 1901. So you know something is important when it's been essentially rediscovered many times and has many names, right? So here's what Wikipedia says. In 1901, it's articulated by Pearson as an analog of the principal axioms theory, and then it was later independently developed by Hotelling in the 1930s. Depending on the field of application, it's also called Calhoun-Burke transform, KLT, in signal processing, the Hotelling transform, the proper orthogonal decomposition in mechanical engineering, and it's closely related to singular value decomposition. And there are other names, empirical orthogonal functions in meteorological sciences, empirical eigenfunction that decomposition, empirical component analysis, quasi-harmonic models, spectral decomposition, empirical model analysis in structural dynamics, and so on. Say in the beginning of the class, most of the tutors have told you what their favorite model is. I would say for me personally, PCA, or when I learned it, I was told this is called Hotelling transform as well in image processing, was my first foray into unsupervised learning, and it was fascinating. For me, it also was the first aha moment of, hey, the eigenvalues and eigenvectors I've been learning are useful. It's also worth noting that the dimensionality reduction literature is vast since the introduction of PCA, but this approach is still the go-to baseline for understanding high-dimensional data. Basically, if you want to do dimensionality reduction, first run PCA and see if that serves a purpose. If not, criticize it and then do something more advanced. So let's jump in. Let's first look at maximum variance formulation. So we have a data set xn goes from 1 to big N, and each of these xn is a d-dimensional vector. So let's just look at finding the best projection direction, the first principal component, such that the variance of the projected data, which is U1 transpose X, is maximized. All right, so we can write down the variance by just writing it out. The variance of a set of data is basically each data point, U1 transpose X small n, minus the mean of this data set, which is U1 transpose the average of X. So the average of the projected data is the projection vector times the average of the original data because of the linear in linearity property of averaging or taking expectations. So this is pretty straightforward. And then we can write this in matrix form quadratically by just taking u1 out of this square and then putting it on either side. So it's basically u1 times the outer product of the xm minus average of x bar summed over n data points, right? Where S is essentially this sum of outer product matrices. So as we said, we will want to just find a projection direction, or U1 is a rotation vector. As we kind of hinted in the eigenvalue overview slide, we will want U1 transpose U1 to be 1. U1 is unit length. And then in subsequent vectors, Ui transpose Uj is 0 when I not equal to j, right? And that's what this part of the Lagrange vector is. Right, so we just changed the objective function by adding this 0 term. And then now we differentiate this with respect to U1 and set the derivative to 0. What this does is for the quadratic term, it's just SU1. And then for the term afterwards, lambda disappears and lambda U transpose U becomes lambda U. Right. So this SU1 equals lambda U1 is a stationary point of the equation 12.4. So this already looks familiar. It's the definition of the eigenvalue and eigenvectors. And furthermore, if we just multiply U1 on both sides, we get that the eigenvalue of U1 is lambda 1. So since we want the projection variance to be maximized, right? So we want to maximize this. We know from 12.6, we know that U1 is one eigenvector of X. We have the freedom, due to this objective, we have the freedom to pick lambda 1 being the maximum eigenvalue of S, and then U1 being the corresponding eigenvector. So that's very simple. We're kind of done. So the maximum variance formulation naturally leads to finding the first projection dimension being the largest. You say, well, in the beginning, you promised finding a set of dimensions if you're operating for more than 2D. Then the next step is essentially sequentially. So after we find U1, we can eliminate that dimension and then just keep doing this, finding the next largest eigenvalue and the corresponding eigenvector and proceed from there.
Wait, sorry.
Yes, okay.
Could I ask a question about last slide? Sorry.
Go ahead.
Yeah, and in this slide, like, I'm not getting why we have known before that U1 is an orthogonal matrix. Actually, Yeah, just like the two lines that you write on the top right corner, as UI transpose times UI equals 1, and UI transpose times UJ when I is not equal to J equals 0. I think at this point we don't have any guarantee about the result that what will be going on here.
That's a good question, right? So if we're only I guess for this slide, what we are concerned with is U1 actually primarily. So since we only care about the projection dimension, the length of U1 don't make a difference in the, like, back to this picture 2 slides ago, we only care about the magenta, where, like, the direction of this magenta line. Then we can, without loss of generality, set the norm of U1 to 1. Is
Okay,
that,
okay.
yeah, is that okay?
U is actually a matrix to adjust the position of those data points, right? And
Yeah, the U is sort of a set of projection dimensions, which we
okay.
will claim after this slide that we do sequentially, or we take the top M dimensions. But on this slide, what we care about is without loss of generality, like the length of, let's say, the length of U1 don't matter. Doesn't matter.
Okay.
Doesn't affect the projection dimension, projection direction. It only affects, right, the value of the projected value of x, but that's not where, like, the maximum variance objective should be sort of considered up to normalization.
Okay, and at the end of this slide, we are getting the expected result of this slide is to get the lambda 1 for the first data point. Is that
for the first eigen dimension? So what this slide means, yes, this slide is sort of a lot of things packed all together. Thanks for slowing us down a bit. So the S matrix here, it has information from all data points, right?
Yeah.
Yep. Therefore, like, all of the subsequent equations on the left have information from all data points. So
yeah.
Yeah, it's using the so we should also just call S, it's a covariance matrix of the data matrix X, where X is basically the data vectors all lined up next to each other.
Yeah, but since I think, oh yeah, I'm still not getting this. Like U1 is only used to adjust the position of X1. I think U1 is going to be multiplied throughout the whole data set. And
yes, you're right. So
and you see the formula 12.5, like S
yep.
like S basically is fixed. If we already assume that U1 is going to be found later, and U1 is going to be multiplied throughout the whole data set, which means S is a kind of in a fixed value here. And when S is fixed, we can basically find all the eigenvalues for each of the data point. Like
so the eigenvalues are only defined for the covariance matrix, basically throughout the whole data set.
okay.
In other words, right, so what's stayed upstairs, right? So let's unpack this, and then I'm going to try and draw a picture in the blank space down here. Hopefully it will help. Right, let's first look at the corresponding parts of this, what's being said here. Variance of U1 transpose X is basically variance of like the whole data set transformed by UN is
Yeah.
maximized, right?
Yeah.
So the transformation is learned with respect to the whole data set. The same deal here, right? So this is essentially variance of the transposed data set,
Okay.
like the highlighted point in yellow upstairs. So this bit and this bit kind of is the same thing. The geometric picture for this in 2D is, I think, like a similar picture will appear later in the slides, but let's just say, like, so suppose we're in the space of x1 and x2, and as we know, we said 2 slides ago, both the latent dimensions and the original variable are Gaussian. So we can now imagine we are looking at 2-dimensional Gaussians. And the stereotypical picture we've been drawing throughout this class is that they are ellipses. The most general case, or the general case of the ellipses, is they are like this, slanted, right? What this does is the original dimension of x1, x2, the covariance matrix is like this, right? Slanted, the 4 elements are non-zero. And the direction of U1, as you can imagine, is basically this. This is the direction of U1. You will find, right, so I'm just going to draw this. So then all of the points are going to be projected down here, right? So the projected points are here, right? From both above and below the line, right? And the variance that we can intuitively see is about like the interval between the two, mean is here, and the interval between the two variants are kind of there, right? And this is sort of bigger than the orthogonal dimension, and in fact, it's bigger than any other arrow you can draw on this 2D plot.
Oh, yeah, I think I get it. And U2 will be the other one, like
yeah, U2 will be like that. Because A, we want U1 and U2 to be orthogonal for good reasons, for computational reasons, and then the only other remaining dimension is perpendicular to that. If we have more than 2 dimensions, then there are more choices of perpendicular dimensions.
Well, this kind of orthogonality will sometimes limit the choice of U1, isn't it right?
Because
we are, yeah,
it
because
will mainly
sometimes,
limit the choice of U2 and subsequent U's.
okay, so
By this.
U1 is always going to be the one that maximize the whole left-hand side, right?
Yes.
Okay.
That's correct. Yeah.
Yeah, thanks.
Yeah. Okay, I'm glad that this helps. So we do have a bit of time today, or like less number of slides than usual. So do interrupt if you want. Okay, so the next slide basically says, we kind of already said, if we want to find subsequent dimensions or a total of m dimensions, it's easy to see that we can, by induction, we can just execute the algorithm or the reasoning on the last slide by picking the eigenvectors from the largest m eigenvalues. Right. Here's another assumption that's sort of left unsaid, but we will like sort of repeat over the course of this this lecture. Is basically we need to remove the mean or center the data before we perform PCA. So it is implicit in the definition of covariance matrices But basically, if we look at this here, when we compute the covariance matrix, the mean is removed by definition, right? And if we look at this geometric picture, we're essentially looking at this point cloud in high dimensions surrounded by the center of it. We don't care where this point cloud essentially are located in the high dimensional space. Meaning, if we shifted this point cloud around with like the rugby balls shaped point cloud, then as long as the direction of the rugby ball is unchanged, it doesn't really matter where the rugby ball is. So remove the mean, compute the covariance of the center data, and then we find the m eigenvectors of the covariance matrix S corresponding to the m largest eigenvalues, and then we're done. So one note about computational complexity is that, so how much time does it take in big O terms to compute eigenvalues and eigenvectors? So this is one of the first things that also tripped me up when I entered grad school and actually need to implement this. It was order of, so for a D by D matrix, which is the size of the covariance matrix, it's order of D cubed. Right, so computing S is order of can someone offer an answer? So the data is, okay, like xn is n times basic D matrix, right? So the S matrix has D squared elements. It's symmetric, but that only halves the number of free elements. So we need to compute each element, so it's at least D squared. And there are n data points. Basically, we were computing the outer product of x, centered x with respect to itself. So there's at least n of those. So computing S costs n times D squared. And then computing all eigenvalues and eigenvectors is a cubic time algorithm in numerical analysis. But if we're computing only the top eigenvector, well, or the top m, like PC dimensions, then it's order of D squared times m. Because if we only want the first eigenvalue and eigenvector, we can use what's called things like power iterations that computes page rank to get the answer. But computing all eigenvalues and eigenvectors is a n cubed iteration. So back at, I guess, my grad school time with a slow computer and one single CPU, the best linear algebra package can do about 4,000 by 4,000 matrix in the matter of a few, well, 10 minutes or so. And that was the largest I can sort of tolerate for iterating on the data. Nowadays, on the current computers and much better linear algebra packages that uses multi-cores and more memory and so on, you can probably do tens of thousands without any problem. Maybe even 100,000. But just be careful if your matrix is, or if your data is 1,000,000 dimensions and you want to do PCA, or 10 million dimensions. So this one more order of magnitude on, say, millions of dimensions, data points will make you wait a bit longer. Right, so there are many ways to approximate, or if you just, when you have 1,000,000 dimensions, more often than not, you don't want 500,000 principal components. as we will see in a little bit. And in that case, just doing the top M components will save you a lot of time. So this is worth being careful when you're implementing this. Most packages will have a EIG function that gives you all eigenvalues, and also GIGS function or something equivalent that only gives you top M. Right? So assume now we have a complete set of orthonormal bases U sub I goes from 1 to D. It's formally written as UI transpose UJ as delta function of I and J, where the delta function basically means it's 1 when I equals to J and 0 otherwise. Basically what we wrote on the top right-hand side of the slide a few slides ago. And what this means is what orthonormal basis means is that any point xn can be uniquely expressed as a linear combination of the orthonormal bases. Basically, for each of xn, there's a set of coefficients a sub ni times ui. If we sum it over, we get back xn, where these coefficients a of ni or nj, doesn't matter the subscript, but it's confusing to switch subscript, I agree, is simply the inner product between the data vector xn times uj. So at this point, you may say, why are we going in circles? What's the point of doing this? So for those of you who have taken linear algebra, which I hope most of you have, this is nothing but just basic linear algebra. And the geometric intuition is as follows. So assume we have a two-dimensional space, X. I'm just going to call, let's say, there was two original basis functions. Maybe I'm just calling it V1. It's actually just has 1 in the first component, 0 in the second component, and V2 is a vector as the opposite, right? 0 in the first component and 1 in the second component. This was the original basis. Or in other words, if we have two components of X, it's just, we usually label the axes as X1 and X2, right? And if we have another set of orthonormal bases, U1 and U2, we can basically, they are just rotations, like this. Right, U1 is like this, and U2 is like this. All right, they are still perpendicular to each other. And the original bases are, of course, perpendicular to each other. And what these equations essentially says is any data point x, right? Any x. In the original coordinate system, it has a unique projection, right? So it's basically the x and y, the horizontal and vertical coordinate system. And then in the new coordinate system, in fact, it's more convenient if we sort of, move them to the origin because shift don't matter. And there is a projection on each of the coordinates too. So this bit is this is the U1, then this is the AN1 and AN2. So we just changed the coordinate system. And this is just the linear algebra way as a reminder to express the change of coordinate system that we've been looking at since high school, I guess. And we just put these two expressions into each other, and we get essentially xn equals the sum over all dimensions, the inner product of itself with ui times ui. All right, this again it may look a bit unintuitive, even if especially when you try and think about removing the bracket, but stuff inside the bracket is a scalar, and it's fine. We can't really remove the bracket and group the ui times ui and so on. Right. Okay. So with that, let's look at the second formulation of PCA, the minimum error formulation, right? So this formulation is a bit more involved. We're interested in approximating x and with up to, let's say, m less than d coordinates, right? And the way we do the approximation is that we have m data-dependent coefficients that are denoted z sub of ni, and d minus m data-independent coefficients bi. You may say, hey, why does it matter? Because we, like, as we said on the last slide, the zni times ui should be essentially the coordinate on the chosen dimensions. And the bi's are there to ensure that basically if we throw away the rest of x, we are not taking into account the mean of x, and then we're losing the opportunity to sort of adjust or minimize the error across all data points x. So we are introducing these bi's that are not dependent on data. And we are interested in the square laws. So we're familiar with this by just plugging in the x and tilde, and then looking at the two norm, the sum of two norm of xn minus x tilde, and call this loss function j, right? And also from the last slide, we know that z of ni or nj are just the inner product between x and uj. And then b of j in here is the average of x and also the corresponding orthonormal basis u of j. So this is obtained by just minimizing j with respect to bj. We get this result. I'm not gonna work through it, and I'm happy to leave this to you to work through in offline. So for now, let's say just trust me and trust the book on this. So if we plug both of these expressions into 12.11, we get this expression j here. For now, we haven't said what these ui's are, but if we plug them in, we see a familiar form again. Basically, the total distortion is at this ui transpose s of ui, that sum over the discarded dimensions from m plus 1 to d, right? And from the eigenvalue equations, we know that the sum of these is equal to the sum of the corresponding eigenvalues. And because we want to minimize this loss, we just pick the d minus m smallest eigenvalues to be part of this loss, and the rest is the principal component, the m principal component. Okay, so this is a very fast skim through of the minimum error formulation. I hope it makes some sense. So we're going to move on to applications of PCA. What can this do for us for a while, and then we talk about extensions. Is there questions about this part for now? All right, let's move on, and feel free to ask questions around the end. So you may ask, so what do the principal components mean, and what do they look like? So assuming we're looking at all the handwritten digit 3s, the mean look like a 3, blurred, because there are shifts around. That makes sense. And the first principal component with the largest lambda, as you can see, the first 4 components have decreasing lambda, but they are all the lambdas of the same order of magnitude. And the blue ink here represent the positive part of the component, and the yellow ink represent the negative part, right? So it's worth noting that the principal component themselves, even if our data is all equal or greater than 0, the principal components is not positive in themselves. They are still real because the eigenvalues are real, the original matrix is real, therefore they're real but not positive. So there are variants that tries to find positive components, or they are called non-negative matrix factorization, but they lose some of the nice properties that PCA have. So, right, the first component basically says the 3 is more likely to be slanted this way than that way. So, or there are basically 2, it captures the rotation, right? So also the coefficients in front of for each component for each data point, it doesn't have to be positive either. So it basically says there are 2 mutually exclusive versions of these 3. One is slanted this way, the other one is slanted that way. And these are almost the extremes of the rotations that the digit 3 can have. The second component covers the shifts, right? So one is the 3 written a bit upwards, the negative one is the 3 written a bit downwards. And the third one sort of separates the foreground versus the background, which is in yellow, right? And the fourth one is kind of the zoom in and out version, right? The smaller 3 look like this, and the bigger 3 look like that. So that's interesting because we can actually interpret the different principal components and they kind of make sense. And these relative magnitudes tells us like the frequency or the relative importance of these different transformations that happen in the data set. You might also think, oh, what do these relative magnitudes look like all the way, right? So these digits are 24 by 24, small digits, I believe. And so therefore they have a total of 676 dimensions. We can see the first few are very big, and then afterwards it drops off very quickly. We can kind of see that, well, above like about 100, the magnitude of these components are quite small. In fact, I would say when we have graphic like this, the linear axis is not the best way to look at them. Log axis probably is, because here they might be small, but still a few thousand. It makes sense though if we look at the cumulative magnitude across all the components. Basically, just do a cumulative sum up to component D of these lambda values. Then we can basically reason about, right, for the top 200 components, the magnitude seem to be like, oh, in here, the cumulative sum is done the reverse way. It basically says if we cut off the bottom D minus n components, how much eigenvalue do we lose, right? And the eigenvalue here also correspond to the square. Well, they correspond to the covariance, which correspond to like essentially the square energy of the signal if you're doing signal processing, which is nice. Basically, it gives a physical intuition to the eigenvalues too. So we can see that in here, if we cut off about after 200, we're not losing very much with respect to the total energy of the signal, right? So there are many things that we can envision PCA could do with us, right? So one thing is called, we can intuitively think about PCA as a compression mechanism. Basically what we said on the last slide, if we only represent the code book, well, we represent the data with m PC dimensions plus the mean. We only need m plus 1 vectors to represent like a d-dimensional vector. So the compressed x is essentially m coefficients each, right? So we work on this a little bit. So the original data is n data points times d dimensions. The compressed data will include n data points times m dimensions plus the codebook of m plus 1 vectors of d dimension. As you can see, if m is a lot smaller than d, the total number of the amount of numbers we need to store is a lot smaller. The book also basically uses this concept. Did I not have a picture of this? Let me see. Oh, okay. Apologies, I forgot to include a picture of this, but I might be able to pull out one. Let's see. So it's figure. So if we do this, what's the picture? It's curious. Yeah, the book basically has a picture of a child, which I suspect is actually the child in the intro, like preamble section of the book, which is the author's family, by basically grouping pixel values. In that case, the savings is in compressing a picture from 24 bits per pixel down to a few bits, right? So there's 1, 3, 5, and 7 bits per pixel. It's 24 bits originally because it has 3 channels RGB, and each is it's expressed in 0 to 255. So it's worth noting that this is by far not the best image compression algorithm, or even a practical image. It is practical, but it's sort of far worse than the JPEG compression that you get, or some of the later compression schemes you get, because it only compresses each pixel independently, and the key of image and video compression is be able to leverage neighboring pixels that are usually similar to each other, both in space and time. Anyway, so that's the I guess, concept of compression via PCA, but it's not a good compression algorithm for especially image and video signal, but for most signals as well. For those of you who are taking or will be taking information theory class, that will happen in semester 2, there is a much better treatment of this, and it also tells you what the limits of compression is. So what PCA does, the next slides talk about other applications, right? One is what's called standardized certain features data set. And so why do we want to do that? Because a lot of times we care about the spread of the data, but not the mean of the data. Assume we are building a linear classifier or regression of data. The mean of the data actually is reflected in the bias terms or the constant terms, the weights for the constant features that we add. It does not affect basically the crucial dimension of the rotation. Furthermore, the mean of one dimension may be a lot bigger than the other dimension, and we really want to remove it before we model, right? So what PCA can do is an important thing is to decorrelate the data, where the covariance of the resulting data is identity. We will talk about this in the next 2 slides from now. It's also called whitening. This is quite important. Why this is the case is that recall the eigenvector equation, right? S times U equals U times, well, they use a different notation again. So L is basically lambda, the big lambda a few slides ago. And the data transformation in matrix form is essentially 1 over square root of U, square root of L in matrix terms. So basically, well, over square root of lambda I, like as a big diagonal matrix, times U transpose with the yn is basically the centered version, the x and with respect to its mean. Right, as you can see, we are from the geometric projection picture, we are remove the mean from the original data set, rotate it or project it to the new coordinate system, and then scale it by 1 over lambda. The intuition from our picture a few slides ago is that we basically go from a rugby ball to the new coordinate, which I'm going to draw maybe slightly differently. So the new coordinate will be like this. And then on the new coordinate, we want it to be a football, basically circular. And that gets rid of coordination, the correlation between different dimensions. Right. So the realization of this is as follows. I realize I have the slides slightly out of order, so let's talk about this one first. So 12.24 is the transformation expression that we just looked at. And then 12.25 is where it's how we show that y is decorrelated and univariance. So this is the covariance matrix of y. Let's call it S of y. It's sum over the outer product of y with itself, right? And we just plug in this expression above, where I just write out to the minus 1 over 2 U transpose x and minus x mean of xn. And then we know that if we transpose a product of different matrices, we just flip the order and transpose everything. So the last term here is xn minus mean of x transposed. U transpose again is u. And then L transpose, taken the negative square root, is L itself because the diagonal matrix is symmetric, right? So we now stare at this whole thing, and we found basically the L part and U part are not dependent on the data xn, so we can take them out of the sum. And if we stare at the sum part, right, 1 over n sum over n xm minus mean of x times its transpose, it's the outer product of xn, the decentered xn with respect to itself. So that's the S matrix with respect to x. And then we look at these matrix product. U transpose S and U is according to the eigenvalue matrix. This is essentially this part is L, right? So we just write L in the middle. Plug it in and stare at this again. Oh, now L cancels out the diagonal matrices, so it works, right? So they cancel out. The result is identity. So that's rather nice, right? So covariance of Y is identity. That means, right, in our familiar Gaussian covariance picture, so the covariance Y, the distribution of Y is ball-like, right? So this is isotropic Gaussian. So the transform data is still Gaussian, but it's now isotropic. So for me, this property is very nice of PCA. What it does is, let's say, this data set on the slide is the old faithful data set, which I believe is the interval and height of the eruptions of the old faithful hot spring in the Yellowstone National Park. So you can see that the data set seem to have two clusters, but if we look at it as a whole, it has this sort of rugby ball structure. There's a principal dimension of spreading here, and then there's a secondary dimension variation roughly here. So the PC dimensions found there look like this. And after the transformation, the whole data set gets stretched, right? So this dimension will become the Y dimension where there's a spread between the two clusters, and then this dimension is where the within cluster spread is. Right? And the whole data set now look more ball-like. Basically, the variance or the marginal variance in the projected dimension become more or less, well, equal, right? So this also says that PCA is good at whitening the data as a whole. It does not whiten the data for each individual classes, right? So that's something else, refers to different objective functions. And in here, we don't know there are two inherent classes, right? Remember, we did briefly mention the Fisher discriminant analysis, where if we know there are two clusters, we could find a dimension that sort of maximize the spread across the two clusters, but that's not what we're doing here. Right, so this is just another iteration of what we just said. So there are two data sets. The principal dimension right, so the 12.8 is the oil flow data set, and this is the projected version. And then people know that there are three classes. There's laminar, homogeneous, and annular flow configurations. But after projection, the green and blue classes can almost completely overlap. And yes, the entire data set is sort of whitened in a sense that, well, the different dimensions have equal variance, but what it does is there's a lot of white space, but there's lots of data that sort of sits on top of each other here. So again, PCA is done without regard to the class labels, and it's not supposed to help separate classes. The example above is even a bit more extreme, that the Fisher discriminant finds this green direction where the two classes are separated, but the PCA finds the red dimension where these two classes are sort of completely overlapped. As we can now see, different objective functions drive very different behavior, right? So let's talk about like more than vanilla PCA, right? What if we have high dimensional data with the number of dimensions greater than the number of data points? So this can happen in practical cases. What I've commonly seen is, say, scenario A, if you're biologist, like if for gene expression data or other bioinformatics data sets, so there's large number of genes where you can measure for each sample, but there's only a small number of samples. So D is in hundreds or thousands, and N is in sometimes, say, anywhere between 10 and 50. So that's relevant. Where the computation is not too much, but the intuition about what you get in these cases is relevant. And case B is, say if you work at Facebook and your D is every single item that has ever come to appear in Facebook in the last few months. So that could be billions. And then N, you still have lots of data, say the user activity in the past week, but that's only millions. Right. So ordinarily, this is just the covariance matrix we've been staring at today all the time in matrix form. And then this is the eigenvalue expression we've been staring at again in matrix form. Right, and then, so if we have D greater than N, we know that solving for all of D eigenvector is bad, especially when D is in billions. And moreover, we know that the effort spent doing so is mostly wasted because there is at least D minus N plus 1 zero eigenvector. We know that the basically the rank of S is at most, or I mean, is the minimum value between D and N. Okay, I wrote that wrong. D and N. So when we've been talking about the case where D is small and N is non-trivial, then we care about D, right? When N is smaller than D, then the rank of S is at most N, and it doesn't make sense to solve for more than N eigenvectors. So what do we do now? So we basically take the eigenvalue equation above and then perform our usual trick of multiplying something to both sides. In this case, we multiply X on the left on both sides. Well, lambda is a scalar, so therefore we can take the X here. And then we do, what we do is we'll just rename X times UI as a new vector VI. Right, turns out they appear on both sides. We just did renaming. We real mathematical induction here. What we can notice is that once we rewrite this expression this way, this is the eigenvalue expression as well, right? So we know that this means that we're looking at a set of the same eigenvalues, lambda I, for a different matrix, right? So for X transpose rather than X transpose X, right? So, okay, and X transpose in now it's a M by N matrix rather than D by D, right? So that's smaller. The next question we ask is, once we are now, we know now we have a different eigenvalue problem. Now what about the eigenvectors? What are they? And then whether or not, yeah, we know that the eigenvalues are the same, then yeah, what's the relation between these two problems? So here is the same equation that we're working on. Now what we do is, since we've multiplied X on both sides, now let's just do it again. Now let's multiply X transpose to both sides. Right. What we do now, we stare at this expression, do the same. Now we have on the left X transpose X and X transpose V and lambda times X transpose V. We do this because this is the covariance matrix of the original vector, original data vector S. And now what we're kind of saying is, we know this, the smaller matrix here, so this is also a symmetric matrix. And we can choose the eigenvectors Vi to be orthonormal. Okay. Now this 1229 is also a eigenvalue expression, eigenvector expression. Basically, these are the new, like these are eigenvectors of S, is a linear transformation of the eigenvectors of the smaller matrix. So we would like to, so we call these U's. We would want to, right, so these are, let's say, Ui primes that are valid eigenvectors, but they're not also normal in the sense that the length is not necessarily 1. In order to rescale this back to 1, we basically say take the direction, and we claim that the scale is 1 over n times lambda taken to the square root. So in the interest of time, I'm not going to show that this is true, but I'm leaving this to yourself. Basically, you can plug, like try and solve for the norm of U by plugging this equation, series of equation back into self. For now, just trust me that we can essentially, what we just said is to solve for the solve for the less than n, less or equal to n eigenvalue. Step 1, vectors vi of x transpose, or 1 over n x transpose. And then step 2 is to linearly transform them into U using the equation 12.30, and then we're done. All right. So there are 2 extensions of PCA we're not going to talk about. Kernel PCA you'll likely see in assignment 2. That covers both PCA and kernels. It's a good, nice thing to play around with. And then for probabilistic PCA, the general thought is basically to explicitly model the latent variable or the PC dimensions or the projected dimensions in an isotropic space, right? We know that they are isotropic. Now that we know, we can specify this in the model. And then we, given that we know the original data is a linear transform of the projected data plus the mean of the original data, we just write it out like this. And this looks quite familiar as the linear models, linear Gaussian models we were looking at in regression and proceed from there. I'm going to cover this. So that's all for today. We've talked about eigenvalues and eigenvectors, and then we used them many times to derive 2 different formulations of PCA. And we also used them to look at the applications of PCA, including whitening. And we looked at one extension of PCA by basically solving for the PCA in a different space and then transforming it into a different, in the original space. So that's all for today. I'm happy to take questions. You can stop the recording for now.